Thank you. Thank you, Angela. And I want to, first of all, thank Angela, Monica, and Miles for the kind invitation. This is a wonderful initiative, and I'm very honored to be part of it. I see that Juan Luis is here, so I'm going to make a ciao, Juan Luis. I'm going to make a premise. I will try not to speak 1 hour as Juan Luis, but I will probably get close to 1 hour. So I'll try to. Okay, so this is. I wanted to share a picture of Bat in Roma. I don't swear that it was the same architect, but I like to think that since this is a one-world seminar, we also have one architect in these two pictures. So what I want to present is some results from recent joint works. In fact, I will mainly focus on 2 of the recent papers with Giulio Tralli. This work revolves around the heat equation in a class of geometric ambients, which besides the mathematical relevance are of considerable interest in the applied sciences. So my talk will probably not be very applied, but I promise that I will not I will not present any proof except a very small one, a very elementary one. So in my talk will mostly be expository. So the geometric ambients that you will see in this talk, they model a physical system in which there is a constrained dynamics. What I mean by this is that motion is, you have Riemannian manifolds, and that's Riemannian geometry. You can move everywhere in the tangent space. In these settings, you can only move in a set of prescribed directions in the tangent space. And therefore, you have what is known as sub-Riemannian versus Riemannian geometry. Elie Cartan was, there is a very important paper by Elie Cartan at the International Congress of Mathematicians in Bologna in 1928, in which this new geometry was more or less formalized. So the key redeeming, so as I said, you cannot move everywhere in the tangent space, but there is some redeeming feature. So you can recover the directions in which you cannot move by taking a sufficiently large number of commutators of the vector fields which describe the PDE of interest. Of course, this complicates life quite a bit, but that's part of the game. So the relevant framework for these PDEs are non-abelian Lie groups. I do not get worried. I will not get into this subject at any depth. So, but these are Riemannian manifolds with a smooth non-commutative group law. So instead of having translations, you have this non-commutative translations. And the Lie algebra of these Lie groups has a special structure. So it has a layered structure, which is suggested by the physical problem at hand. For instance, you know, if you look at the physics of polymers, so then there is a very well codified way of you know, deciding what is the structure of the Lie algebra. So, so the most important of these Lie groups is the ubiquitous 2n+1 dimensional Eisenberg group. I will talk a little bit about this ambient later on. This was first introduced by Hermann Weyl in his approach to quantum mechanics. He developed an approach to quantum mechanics based on group representation theory. And so it was called the Weyl's group, but was subsequently rechristened by mathematician Heisenberg group. So this Eisenberg group is equipped with a conformal invariant partial differential operators of order 2, which is known as the horizontal Laplacian. And I will be particularly interested in fractional powers of these operators. I mean, it's a natural question to ask whether the natural powers of this important operator retain the same geometric properties that L, the horizontal Laplacian, does. And unfortunately, unlike what happens for the fractional powers of the standard Laplacian, this pseudo-differential operator does not preserve conformal invariances of the local operator. So one has to look for something else. And my focus in this talk will instead be on a class of non-local operators which are conformal invariant in Hn, or more in general in Lie groups of Eisenberg type. And again, don't get scared by the language. This is a class of, an important class of Lie groups which are modeled on the Eisenberg group, and they arise in many questions in geometry. So the non-local operators that I will be interested in will be denoted by this L lower S, as opposed to the L upper S, which denotes instead the fractional powers of the horizontal Laplacian. Okay, so this is just a preface, so I will not, you know, put any definitions at this moment, but I will give you some definitions as we move on. So the objective of my talk will be to present a new approach based on the heat equation and some variants of it, to prove the invertibility of these fractional powers. So this is one of the basic problems in analysis. We always worry about finding the inverses of the relevant operators, to find explicit formulas of the fundamental solutions of these operators, and finally to prove some intertwining formulas for L lower S, which are connected to conformal Yamabe, to the fractional Yamabe problem. And the problem is indicated here. So the meaning of the word intertwining and the meaning of this number Q, which you see for people who are familiar with the fractional, with the standard fractional Yamabe problem, you see that this number Q is playing the role of a dimension, will be clarified later in my talk. So I usually put a list of an essential a list of references in my talks. So there are some very important papers here. Other are less important, and they are put at the end of the list. So, but these are the papers: the Folland, Cowling, Agerup, Frank, Rupert Frank, and Elliot Lieb, Branson, Fontana, Morpurgo, Rupert Frank, Maria del Mar Gonzalez, Daniele Monticelli, and Tan, Roncal and Tangavelu, especially in particular, these two papers have been very influential in our works. So, and then there is a series of papers with Giulio Tralli, and these are the papers that I'm going to be discussing in this talk. So I will start by discussing a model. So model question related to part 3 of my talk, intertwining formulas. So let's consider an old friend. Juan Luis has introduced this operator in his lecture last week. The fractional Laplacian. I will start with the Fourier transform formulation of it. As we all know, this is equivalent to the Marcel-Ries 1938 definition of the fractional Laplacian. So then this formula holds. This is a first example of an intertwining formula. Intertwining here means that if you change S into minus S, you find this formula reverses into a formula which is equivalent to the original one. So, so there is this nonlinear equation which is satisfied by this quantity here. So if you take the standard fractional Laplacian of this function here, here x runs in Rn and y is an arbitrary positive number. If you don't like the y, you can just put y equal to 1 because this equation is invariant under scalings. And so if you put y equal to 1, then you recognize some old familiar functions, the Aubin Talenti Lieb functions in the Sobolev embedding theorem. And so there is this equation here that holds. And a direct proof of that equation is usually given by Fourier transform. And ultimately hinges on some integral formulas involving special functions. If you are interested in seeing a proof by Fourier transform, you can look up this reference here. Such proof, the one by Fourier transform, was implicitly known at least since the celebrated 1983 work by Elliott Lieb concerning the best constants in the Hardy-Littlewood-Sobolev inequalities. And one immediate consequence of this equation is that it provides a one-parameter family of solutions to the non-local Yamabe equation. You see it immediately because if you raise the right-hand side to the appropriate power n minus 2s over 2, then you get up to renormalizing the constant, you get a solution to this equation here, okay? So that equation arises in many questions concerning the fractional Laplacian, questions of invertibility, questions of finding the fundamental solution of the fractional Laplacian itself. And of course, it arises in connection with this nonlinear equation here. So let me briefly recall the Cafarelli-Sylvester extension procedure. This is a very famous procedure. Most people are familiar with it. So you solve this problem in the thick space Rn cross Ry. I'm sorry, here there should be a plus. And then the connection between this problem here, so the solution to this problem, capital U, and the fractional Laplacian is provided by the following Dirichlet to Neumann relation. So, and you see that in this problem, the Bessel semigroup, which is this part of the operator, which has infinitesimal generator, this part of the operator plays a very critical role. You have the Bessel semigroup with the Neumann condition 0 in y equal to 0. So this corresponds to reflected Brownian motion. And I have recalled this problem because, as you will see very quickly in my talk, some form of extension problem, in particular a parabolic extension problem, will play a pervasive role. So in fact, to motivate the main theme of my talk, let me present an alternative this formula here, which is not based on Fourier transform, and does not use, of course, the theory of special functions. So I will give you a very simple proof based purely on the heat equation. So let's consider, instead of the fractional Laplacian, the fractional heat equation. The extension problem is this Dirichlet problem. Notice that I'm calling it a Dirichlet problem because it is a Dirichlet problem, despite the fact that this is an evolution operator. So this is the analog of the Cafarelli-Sylvester extension problem. This problem was first introduced in the case S equal 1/2 in a beautiful, although not so well known, 1968 pioneering paper by Frank Jones. And in fact, Frank Jones even constructed an explicit Poisson kernel for this problem. More recently, Nystrom and Sande and Stink and Torrea independently generalized Jones' result to the case where S is any number between 0 and 1. But in essence, you will find you know, a great deal of the ideas in this paper by Frank Jones. So now I make the claim that the conformal invariances of the equation 0, 1, so the intertwining equation, are embedded in the fundamental solution of this parabolic operator here. So now if you look at this parabolic operator, you see that it is essentially, it's a heat equation. Why? Because if we consider W to be a vector in the fractional space R2, 1 minus S, and we take Y to be the length of this vector W, then the operator P upper S represents the action on functions with the cylindrical symmetry. Notice that I'm taking functions that depend on the length of W, so on Y, of this heat operator. So it's well known, right, that, you know, the Laplacian on a spherically symmetric function becomes the Bessel operator. And the dimension is correct, because if we take 2, 1 minus S minus 1, we get exactly 1 minus 2S. So the fundamental solution of this heat equation, heat operator here is given, as we all know, by this function here, which I'm going to rewrite like this. And the P now is the standard fundamental solution of the heat operator Laplacian x minus dt. So I will denote by Q upper minus S, the heat kernel obtained by replacing S into minus S in this formula here. And then we know that by Bochner's subordination, the integral in time of the fundamental solution of the heat operator provides us with the fundamental solution of the time-independent differential operators written here. One of them is the Cafarelli-Sylvester operator. The other one is the intertwined operator. So now we use the elementary but very important consequence of 0.5 that says that the integral, we compute explicitly this integral, and it's given by this formula here, right? So this is just an elementary computation. And then in view of this, the problem of proving 0.1 now is reduced to that of establishing the equivalent dimension-free intertwining relation minus Laplacian S of E upper S equal to this normalizing factor times E minus S. So I can reformulate 0.1 into this form here, where E upper S and E upper minus S are the two functions produced by integrating this fundamental solution in time. And now you see that the game now is to prove this. Okay, to prove this, I will resort once again, I will bring to center stage once again the heat semi-group. And instead of using the Fourier transform definition of minus Laplacian to the S, I will use the Balakrishnan, this beautiful formula, which goes back to Balakrishnan, 1959, in his PhD thesis, which actually dates 1954 with Ralph Phillips. Balakrishnan found a way to write fractional powers of closed operators on Banach spaces. And if you apply that to the specific case of the Laplacian, you get this formula here. And then in this formula, you can integrate by parts once and write it in this equivalent form. So now I want to apply this to U equal to E upper S dot Y. So if I do that and I use the semi-group property of the heat semi-group, so the Chapman-Kolmogorov equation, then I will get this. notice I need to compute pt of this function now to get this thing here. So at this point, we make this change of variable and integrate by parts, and we obtain with very elementary computations. They're written here. You see here, I'm changing variable. Going from here to here, I change variable. Going from here to here, I integrate by parts. Going from here to here, I just write the derivative of this function. And then finally, going from here to here, I apply Fubini's theorem and I exchange the order of integration. So minus Laplacian to the s of E upper S is given by this expression here. But this expression is very simply computed by noting that this integral is equal to this. We substitute this information in the previous formula, and we immediately reach this conclusion, which proves formula 0,1. Okay, so the objective of my talk is to present some version of 0,1 in which minus Laplacian to the s is replaced by the conformal fractional horizontal Laplacian in the Eisenberg group, or in a more general in a Lie group of Eisenberg type. And this is now the time to introduce the relevant geometric framework. So I will quickly tell you what the Eisenberg group is. Just think of the Eisenberg group as R to the 2n plus 1. Okay, so this group, you can describe it also as a group of upper triangular matrices. In fact, in the original quantum mechanics formulation of Weil, the Eisenberg group was described as such. But anyhow, so let's consider the symplectic matrix J. So this is so these are blocks in of n by n matrices. So if we apply in R2n plus 1, I will denote the variables like this. So I will split R2n plus 1 as R2n with respect to variable z, direct sum with R with respect to variable sigma. Usually the Eisenberg group is denoted with variables z and t, but I want to reserve t, of course, for time, and therefore, because I'm going to be using the heat equation a lot, and so I'm using this variable sigma. So I apologize for the with the Eisenberg group aficionados. I hope that this doesn't throw anybody off. So let me introduce this multiplication law in R2n plus 1. So you see nothing happens here. This is just the standard Euclidean translations. In the variable sigma, there is this strange thing. But with this object here, this is a non-commutative group law. And with this object, R2n plus 1, endowed with this multiplication, becomes a Lie group. And it's called the Eisenberg group. So I will denote from now on generic points in Hn with z sigma, z prime, sigma prime. It's easy to compute the identity element with respect to this group law is just the origin, as in Rn. So you have to think of this as translations. And therefore, from now on, I will denote L sub g, the translation to the left, by the element g. And if you compute the differential of this Lg and you apply it to the elements of the standard basis of R2n plus 1, you end up with this 2n plus 1 vector fields. So by definition, these vector fields constitute a, they generate the whole algebra of left invariant. So in vector fields which are invariant with respect to this left translation here. And they are written here. Now, in mathematics, there is an important operator which is attached to these vector fields. And in order to define it, we only use this x1, x2n vector fields. There is a little problem, though. These vector fields do not span the whole tangent space. You see it very easily at the origin. If you freeze them at the origin, you're missing the direction dd sigma. But there is a redeeming feature. With one commutator, you generate the missing direction, dd sigma, okay? So this is, of course, it's the quantum mechanics commutation relation for position and momentum. And so now the horizontal Laplacian, or the Conspenser sub-Laplacian, or the real part of the Conspenser sub-Laplacian, is the sum of the squares of this vector field. And you write it explicitly, is this partial differential operator now in the variables, remember that z is x and y. So you have this partial differential operator in R2 n plus 1. And this is going to be our Laplacian, okay? So this operator, unfortunately, fails to be elliptic at every point. If you compute the eigenvalues of the quadratic form, you see that one of them is identically equal to 0. However, according to a celebrated 1967 theorem by Ormander, and because of this commutation relation here, this operator is hypoelliptic. So it shares the same property as the standard Laplacian. So distributional solutions of L of u equals f are C infinity wherever f is C infinity, wherever the right-hand side is infinity. So we have this breaking of the Lie algebra in layers. There is R2n, and then there is R sigma. So the second layer, R sigma, which I will call the vertical layer, has weight 2, because we need a vector field of order 2. We assign a degree to commutators. So if I take a vector field, that's a commutator of order 0, or 1, if you wish, actually 1. One commutator is a vector field of order 2. So the dilations have to respect this layering of the Lie algebra. And so instead of the standard homogeneous dilation, I'm going to take this non-isotropic dilations. And it's easy to verify that this operator is of order 2 with respect to this dilation. So it interacts well with these dilations. So these dilations immediately identify a number, which is this one. This number is bigger than the topological dimension, because the topological dimension is 2n plus 1. And the Lebesgue measure interacts with these dilations according to this formula. So for all practical purposes, you have to think of this number as a dimension. And in fact, it has a name. It's called the homogeneous dimension of the group. Okay, so, and the role of this, the important role of this dimension will be particularly underscored by the following result of Folland, which I'm about to quote. So there is also a norm. Think of this as an equivalent, never mind this 16. 16 comes just by normalizations that I've chosen in the group law. So there is a norm. So you see this norm scales well with respect to the dilations, to the non-isotropic dilation lambda lambda square. This norm is homogeneous of degree 1. It's called the Korani gauge, usually. And there is this beautiful theorem by Folland that goes back to 1973, if I remember correctly. I know it's written on the slides, but I cannot read my slides because I see all the some of your pictures there. So Folland's theorem says that the fundamental solution of this horizontal Laplacian is given by this object here, this gauge, to the power 2 minus q. This is quite remarkable, right? Because, you know, if we go back to the fundamental solution of the standard Laplacian, at least in dimension bigger than or equal than 3, you see that this is completely analogous to this if we let q play the role of the dimension n. And so one gets very, this result by Folland is not just a mathematical curiosity. It played a fundamental role in a program that was laid out by Eli Stein at the International Congress of Mathematicians in Nice in 1970. And it's, I will come back to that function. So, and I will also come back to Folland's result at the very end of my talk when I will show you that running the heat flow in Hn, we can actually discover the magic gauge function and recover Folland's theorem in the limiting case as tending to 1 of a family of fractional theorems. But these fractional theorems will not involve the standard horizontal Laplacian that I have written here. Okay, so there will be a theorem, but it will what the relevant fractional powers will concern an operator that is different from that one. So let me summarize then for everybody the situation of the Eisenberg group. So the Lie algebra is decomposed into 2 layers. One is V1, which is R2n with respect to the variable z cross 0 with respect to the variable sigma. And I will call this the horizontal layer. And then there is a vertical layer, which is z with respect 0 with respect to the variable z Cartesian product with R sigma. These 2 layers satisfy the property that the bracket between V1 and V1 is equal to V2. This is codified by this commutation relation. Okay, and then V1 bracket V2 is 0. This is so-called nilpotency property. So because of the splitting of the Lie algebra in 2 layers, Hn is a model, in fact, is the quintessential prototype of a class of groups which are known nowadays as Kernel groups. And this is an example of a Kernel group of step 2, because the Lie algebra breaks into 2 layers. If you have a breaking of the Lie algebra into R layers with the appropriate assumption that you keep generating the subsequent layer every time you bracket up until a certain maximum number R, after which you have nilpotency, then this is called the Kernel group of step R. And there is always a horizontal layer, which is the first layer in the stratification of the Lie algebra. So these are algebraic assumptions on the Lie algebra that convert into very important differential consequences for the PDE involved. So to introduce my first result, now let me consider a general Kernel group. I just told you what they are, so never mind, you know, if we at this moment we have a very superficial glimpse in what these objects are, but so there are these Lie groups, and there is a well-known heat semigroup defined on this group. This was constructed by Folland himself in 1975. This semigroup is stochastically complete. So this means that PT of 1 is 1, like for the standard heat equation, okay? So if we integrate this function with respect to 1, we get 1. This semigroup is all that is needed to study the fractional powers defined in this way. So I take minus L to the S. L here is a fixed horizontal Laplacian associated with 1 orthonormal basis of the first layer, the horizontal layer. So we are missing lots of directions, but there are commutators that will help us. But I will not go into at all now into any detail, and simply tell you that Balakrishnan formula again comes into help in defining these fractional powers. And it's, you see, it's exactly what for what we do for the standard fractional Laplacian. So we take the heat semigroup, and this integral is always convergent because PT UG minus UG, you can prove for a function in C0 infinity is a big O of t. as t goes to 0. So this integral is like 1 over t to the s near 0, and so it's convergent. At infinity, this is a semi-group, so 1 over t to the 1 plus s is convergent. So this object is always well-defined. Okay, so with such formula in hands, now it's very easy how to invert this pseudo-differential operator. So let me show you what is the standard way of inverting this pseudo-differential operator. So let me introduce the Riesz potentials. So instead of using the standard definition of Malser-Riesz, I will use the heat equation based notion of Riesz potential. If you specialize this to the standard Laplacian, you get exactly the Riesz potentials that were introduced by Marcel-Riesz. So using this object, it's easy to prove that I upper to S inverts LS, upper S. And so these operators are the inverses of the fractional powers of the horizontal Laplacian. And in particular, this tells us, this formula tells us that if we take the kernel of this operator, which is given by this function here, we get a fundamental solution of the operator L upper S with pole at the group identity. Okay, fine. So when the Lie group is abelian, so let's return to the familiar ground of Rn. So if the Lie group is simply Rn, so this would be the trivial case for what I'm telling, because we're back into the abelian situation. Then integrating this kernel here, if we integrate the standard heat kernel, we get a familiar object. So this is the classical formula that gives us the fundamental solution of the fractional powers of the Laplacian. Okay, so this result and the Folland's theorem, in the one that I quoted you, in the local case when S is equal to 1, might lead to believe that in the Eisenberg group, the fundamental solution of this fundamental solution here, so when you integrate the heat kernel, you should get a formula like this, right? Compare it with this. We've seen that when S is equal to 1, this formula does hold and does give us the fundamental solution of the horizontal Laplacian. Well, unfortunately, this guess is completely wrong. The distribution defined by the right-hand side of this equation is not a function which has gauge symmetry. So it's not a function of the gauge, like in this wishful formula, except in the limiting case as S goes to 1. So you can only recover the limiting case, but not the fractional case. So as I mentioned in my preface, there is another pseudo-differential operator, which I had said before I will indicate with L over S. Actually, this notation goes back to a paper which I have quoted by Rupert Frank and Elliot Lieb. So very different from L upper S, and whose fundamental solution does instead give us a formula such as this one. But this is where my story begins, okay? So let me give you a little glimpse of what will come, but this is only part of the story. There is much more to it. So as you will see, right. So I have to speed up, otherwise I will beat Juan Luis in overextending my welcome. So anyhow, so if we take the standard Laplacian and the standard Laplacian to the S, we have this fundamental solution. These two operators conformally change. They are invariant under conformal changes. This does not happen in this ambience. So in the Eisenberg group, the operator L upper S is not conformal, but in order to restore conformality, so important geometric properties, we have to look at this operator L lower S. So, well, at this point, I need to define for you L lower S. Unfortunately, the definition of this operator is not so simple. And it was first introduced in the cited 2013 paper by Bramson, Fontana, and Morpurgo. And the operator is introduced via a spectral formula. This is Euler gamma function. Okay, so you have to think of this in terms of spectral resolution of the operator. And T here, L is the horizontal Laplacian in the Eisenberg group, and T is the dd sigma, so it's the missing direction. So it's very simple to check just formally using the standard important property of the gamma function, the factorial property, that when s is equal to 1, you see when s is equal to 1, this term drops. And if we put s equal to 1 here, we have plus 1. So if we apply formally this thing, we're going to get minus 1/2 L to t to the minus 1. When we multiply by t, multiplied by 2, we get that L1. If we put s equal to 1 in this formula, we get minus L. However, for s between 0 and 1 strictly, this operator is very, very different. It has very little to do with minus L. So this operator was introduced by Bramson, Fontana, and Morpurgo, and I will not use this definition of L lower S because that will that put me immediately into a almost compelled track that will prevent me from using in an effective way the properties of the heat equation that I have hinted in my introduction. So there is this very important paper by Rupert Frank, Maria del Mar Gonzalez, Daniele Monticelli, and Tan, in which they've introduced a so-called CR extension problem for these fractional powers L over S. So given a function f in C0 infinity of Hn, to find a function capital F in the Tick space such that this problem is solved. So here, once again, L is the horizontal Laplacian. And notice that if the term in blue was not there, that would simply be the Cafarelli-Sylvester extension problem for L. And so we would be back into the standard fractional power L upper S. However, there is that term. That term complicates matters considerably, but also introduces a geometric meaning into the problem. And I hope to convince you of this as my talk goes on. So Frank and his co-authors proved a very important Dirichlet-Neumann relation that mirrors the one which is in the Cafarelli-Sylvester extension theorem. And now we are dealing with this operator, with this very strange looking operator here. Okay. Oh, by the way, I did not tell you before that when S is equal to 1, also L upper S coincides with minus L. So the two operators, L lower S and L upper S, they do coincide only in the limiting case, S equal to 1, but they are otherwise incredibly different one from the other. All right, so in their cited works, Roncal and Tancavelo used a parabolic version of the extension problem to establish some beautiful Sharp-Hardy inequalities. And Giulio and I, in the works that I have cited at the beginning of my talk, were much inspired by these works of Roncal and Tancavelo. And in fact, we're going to be using in a systematic way the parabolic extension problems. And we combine it with other ideas. And so anyhow, so I will skip this slide because in this slide, I simply define Lie groups of Eisenberg type. So if you are curious, you can look at it, you know, once that my talk is over. I just want to emphasize that from now on, you have to think of the vertical layer not just as being composed of one dimension in sigma. Now there is going to be k dimensions in sigma, and so the homogeneous dimension, the one attached to the parabolic dilations, is going to be m plus 2k. So that's the only thing that you need to keep in mind. So heat kernel. So in the Eisenberg group, or in a group of Eisenberg type, the heat kernel has a very important, almost explicit representation given by this formula. This was found by various people, and I give credit to all of them: Hulaniki, Gaveau. In the late 70s, found this fundamental solution, and then it was subsequently generalized by Chigan, who at that time was a student of Ulanigi, to all groups of step 2. So I'm going to build on variants of this formula to define L lower S. So remember, I will not use the strange formula. So I will consider this parabolic extension problem, which once again has this blue term here. If this blue term was not here, so this would simply be a parabolic version of the Cafarelli Sylvester. So this is the version originally studied by, you know, it's, I already told you the story. So the big fact here is that the fundamental solution of this operator P lower S can be computed explicitly and is given by this, you know, explicit up to an integral. You see there is a Fourier integral here in the vertical layer. So this is the vertical layer of the Lie algebra, but it's an integral. You can work with it. Okay, so the origin of this function can be explained by the fact that this operator PS can be viewed as a special Bawendi-Grushin operator, and you know, in order to recognize this, you have to go a little bit into the guts of what is the expression of horizontal Laplacian in a group of Eisenberg type. So the PDE can be written explicitly in this form, but in the end, you come up with this equation here. So the extension equation can be written in this form on some special function. So functions which are spherically symmetric in the variable z. This is the horizontal variable. Once you see this, this is a parabolic Bawendi-Grushin equation. If DDT was not there, this would be the operator of Bawendi in his thesis under Malgrange in 1968. And we computed in this paper, written at the bottom here as a footnote, we computed explicitly the fundamental solution, and it's given by this function here. So with that fundamental solution, now we can write also the intertwined fundamental solution. So the one obtained by changing S into minus S. So there is an operator P lower minus S. And these are the intertwining relations that connect the two operators, okay, with the respective fundamental solutions. Okay, so now from Bochner's subordination principle, as for the standard Laplacian, if we integrate in time these objects, we're going to get the fundamental solution of the operator of Frank, Delmar Gonzalez, Monticelli, and Tan. Okay, so this leads me to the first main result of my talk. So there is this monster constant, explicit constant. So keep in mind this formula here, because you will see it in the next theorem. So first theorem tells you that if you integrate in time this object, so you obtain this explicit function. Okay, so let me state immediately that if you remember, maybe you won't at this moment, but if you look back at my notes, this theorem is the counterpart of the almost trivial but fundamental formula with which I started my talk. Except that now there is no gauge symmetry here. You see, in order to have the gauge, you should have y equal 0. But there is no gauge symmetry, but it's important that there is not gauge symmetry for a very important geometric reason. And so this is our first theorem. We computed explicitly this, this object here. The proof of this is not as simple as this one, but you can look at it in. With the previous theorem in hands, now we can state, I can state the second main result. The second main result is that L over S of this function is equal to this. So you see a complete analogous of what happens for the Laplacian, except that now I'm using this monster operator here. Once that you have the previous theorem, this one, and this one, then we immediately obtain our third theorem, which is the conformal invariant intertwining formula. And this is the counterpart of the one that I started my lecture with. Okay, so, well, at this point, you immediately see from this formula that this formula provides a family of solutions of this non-local CR, conformally CR Yamabe equation. This equation has been studied indirectly in the important work of Rupert Frank and Elliott Lieb, which I quoted at the beginning. And also, it was studied in the case S equal 1/2 by Jerrison and Lee in the early 80s. They have some fundamental work on the CR Yamabe problem. All right, so I will skip this and skip this, and I guess that let me quickly jump to the conclusion of my talk. So we are able to construct using a different, the intertwined operator. Remember, so the whole thing now is that I haven't told you what L sub S is. For us, L sub S is going to be an analog of Balakrishnan formula, given by where now the heat semi-group has been replaced by this object. And in order to go into the guts of this object, one has to look carefully at some, you know, at these extension problems. So I don't have any time to go into this, but I want to only tell you that P lower minus S is given by this K lower minus S when you put minus S in here. And P lower S is given by the corresponding one where there is this K here. And these have some precise meaning. So then we can construct, using this PS, we can construct the Rees operator. Notice that here there is this PST, and instead in the definition that we use of L over S, there is P minus S. Neither one of these two operators is the same. So there is some difficulties there, but we are able to invertibility formula that parallels the one that I told you for L upper S. And then with that invertibility formula, I mean, we're also able to prove, compute explicitly, and this is my last result, fundamental solution of L lower S is given by this integral here, which, notice, produces us precisely the appropriate power of the gauge. And when S tends to 1, all constants will tend to the correct constant, and we recover the proof of Folland's remarkable formula for the fundamental solution of minus L, but I've already taken up too much of your time. Thank you very much to everybody who has been so kind to resist up to this moment.